Yeah, I think we have an audience, and okay, I think we can start. It's 2:00 p.m. Okay, it's the right time. Good afternoon, all. Welcome to the second technical session of SBMF. This section has 3 works. All of them propose model checking approaches. Nothing more appropriate after the last tutorial about model checking. Before we start, just to remember, the presenters have 20 minutes. And after we have time for questions. Okay, so let's start with the first work about model checking and strategy synthesis for multi-agent systems for resource allocation. Nils, you show a video of his presentation, and after the video, we will open for questions. When ready, you can start, Nils.
Welcome to my talk. I present joint work with Josua Botha on model checking and strategy synthesis for multi-agent systems. I start with an overview of the systems that we are looking at, which are multi-agent systems for resource allocation, or briefly MRAs. Such a system consists of a set of autonomous agents and a set of resources. In the depicted example, we have the agents A1 to A4, and the resources R1 to R5. Each agent has access to a subset of the overall set of resources, indicated by the edges here. As we can see, resources can be exclusive. For instance, agent A2 is the only agent that can access resource R4, or resources may be shared. For instance, resource R1 is shared by the agents A1 and A3. We assume that each agent has a demand, which is an amount of resources it has to allocate over time in order to perform some computational task. For instance, agent A1 needs to hold 2 resources in order to perform its task, whereas agent A4 only needs 1 resource. In order to get their demand satisfied, agents perform actions in discrete rounds. In each round, each agent chooses an action, and this tuple of actions is then executed simultaneously. In the example, we have that in the current round, agent A1 requests resource R1, agent A2 requests resource R3, agent A3 requests resource R3 as well, and agent A4 requests resource R5. The outcome of the execution of such an action tuple is the transition of the system into the next state. And a state corresponds to an allocation of resources to agents. A resource can be either available or currently allocated by some agent. We use an operational model where an available resource that gets requested by exactly one agent will be allocated by this agent in the next state. And a resource that gets requested by multiple agents will be allocated by neither of these agents in the next state. In the example, we have that agent A1 was the only agent that requested resource R1, so in the next state, A1 will hold R1, which is indicated in red here. Multiple agents requested resource R3, so this resource will be not allocated by any of those agents in the next state. And R5 was only requested by agent A4, so this resource will be allocated by agent A4 in the next state. Now let's consider a second round of actions by the system. The first agent idles, which is also an option. The second agent requests resource R4. The third agent requests R3. And the fourth agent releases all of its allocated resources. It will do this because it has already reached its demand in the current state. Now the resulting state looks as changes for agent A1. agent A2 now holds resource R4, agent A3 holds resource R3, and agent A4 does not hold any resources in the current state. We assume that agents can autonomously choose actions that are available to them in the current state. Availability, for instance, means that agents can only request resources that they can access and that are unallocated in the current state. In a longer run of the system, each agent has a goal to reach a state where its demand is satisfied. In multi-agent systems, it is a common assumption that a coalition of agents collaborates in order to achieve their collective goal, and they have to achieve it against an opposition of agents. For our example, we assume that the coalition A are the agents A1 and A2, and the remaining agents are the opposition B. Now, a corresponding model checking problem is to determine whether the agents in the coalition can choose their actions such that they will achieve their goal, irrespective of how the opposition acts. If this goal achievability is possible, then we want to synthesize a corresponding strategy for the coalition, which tells each agent in the coalition which action to select in which state of the system. This slide here summarizes what we have illustrated so far based on the example. A path of a multi-agent system is a sequence of states connected via transitions, and the transitions are caused by the execution of action tuples. The goal phi A of a single agent A is to reach a state where its demand is satisfied. The collective goal phi of a coalition is that eventually each agent of the coalition reaches a state where its demand is satisfied. A strategy of a single agent is a function alpha A that assigns to each state of the system an action to be selected in this state. A joint strategy of a coalition is a tuple of single strategies, one for each agent in the coalition. And we call such a strategy a winning strategy if, when the coalition follows it, then the collective goal will be achieved no matter of how the opposition acts. Finally, the corresponding model checking problem is to determine whether the coalition A has the winning strategy for phi, and also to synthesize such a winning strategy if it exists. The crucial part of this model checking problem is that the winning strategy needs to succeed against all possible strategies of the opposition. So the synthesis of winning strategies is computational complex, because we have that obviously the state space is exponential in the number of resources, but additionally the number of possible strategies is exponential in the number of states. Before we look at our approach to this model checking problem, we have a look at a few related problems that can be defined. The original problem is shown at the top. It asks whether the coalition A has a strategy that guarantees that the collective goal will be achieved against all possible strategies of the opposition. Now we can also define the so-called complementary problem, which is, does the opposition B has a strategy to prevent the goal against all possible strategies of the coalition A? We have that the original problem holds if and only if the complementary problem does not hold. For both the original and the complementary problem, we can also define the following restricted versions. In our restricted original problem, we assume that we have given a fixed set sigma of strategies of the opposition B. And the problem is whether the coalition A has a strategy that guarantees the goal against the strategies in the set sigma, but not necessarily against all strategies of the opposition. In the same way, we can define a restricted complementary problem. We assume that we have given a fixed set sigma prime of strategies of the coalition A. Now we ask whether the opposition B has a strategy that prevents the goal against the coalition strategies in the set sigma prime. As a remark on the restricted problems, we can say that for small strategy sets sigma and sigma prime, the restricted problems are much more tractable in terms of complexity. Moreover, we have that the following theorems are true. As already mentioned, the original problem holds if and only if the complementary problem fails. We also have the restricted original problem fails implies that the unrestricted problem fails. In other words, this means that if there is no winning strategy against a small set sigma, then there cannot be a winning strategy in the general case. And the final theorem here is the restricted complementary problem fails, implies that the unrestricted original problem holds. This means if the opposition cannot prevent the goal against a small strategy set, then the opposition cannot prevent the goal in the general case, and consequently there must exist a winning strategy for the coalition. We will now see how we make use of these theorems in our approach and how it helps us to solve the original problem based on a number of restricted problems. I will now step by step construct a big picture of our iterative approach to the MRA model checking problem. First, we initialize a set sigma with some greedy strategy for the opposition B. And then we solve the restricted original problem with regard to sigma, which is, does the coalition A has a strategy to achieve the goal against the opposition strategy in the set sigma? If this fails, then we can immediately conclude that also the original unrestricted problem fails. If the coalition has no strategy that succeeds against the opposition strategies in the current set sigma, then the coalition has no strategy that succeeds in the general case. Succeeds against the opposition strategies in the set sigma. In this case, we synthesize the problem. We check whether the opposition B has a strategy that succeeds in preventing the coalition from reaching their goal if the coalition follows the strategy alpha. If the opposition has no such strategy that succeeds against alpha in terms of goal prevention, then we can conclude that alpha is the winning strategy for a coalition, which guarantees that their goal will be reached. So this alpha is then a universally winning strategy for the coalition A, and the unrestricted original problem holds. But if the restricted complementary problem holds, then we can synthesize a strategy beta prime for the opposition B that succeeds against the coalition strategy alpha in terms of preventing the goal. It means if the coalition follows the strategy alpha and the opposition follows the strategy beta prime, then the coalition will not reach its resource allocation goal. What we will do in this case is we will start another iteration of our approach. We add the synthesized opposition strategy beta prime to the set sigma, and then we check whether the coalition A has the winning strategy against the extended set sigma. So basically we repeat all steps of the previous iteration, but now for a set sigma that contains one additional strategy of the opposition. Now either we get a definite outcome in this iteration, or we continue with further iterations in the same manner. Our iterative loop will at some point terminate because the number of possible strategies is finite. In the worst case, we would have a sigma, but in several cases it is in fact possible to achieve termination for a very small sigma. Allows to solve the problem of MRAs based on several less complex restricted problems. Discussed our multi-agent systems and dynamics a bit more formally. And I will also answer the question of our algorithm.
I'm not sure if the problem is my network of because it's the audio is fading.
Problem?
Looks like there's a problem with the connection.
Nils has lost his connection. We wait for some few minutes. Let's see if it's possible to reestablish.
Yeah. If it doesn't work, if it took too long, we can start with the second presentation, then he comes back later.
Okay. Did him send the video? Because if we had the video, we could play.
No, unfortunately not.
We have a 10 minutes slot for questions. Maybe if we return in some minutes, in a few minutes, we can conclude his presentation and maybe the questions we will just do 5 minutes, I think.
Sure. Maybe you would like to proceed with the second presentation.
Yeah, I think it's a better. It's a good idea. Okay, so due to technical problems, we lost the connection with Nils. He was presenting the first paper of the section, and let's see if he's able to return and we have enough time to conclude his presentation. But what we can do now is to go to the next presentation, next work. A two-level approach based on model checking to support architecture conformance checking. I think Bruno will present this work.
Yes, I'm gonna share my screen. Can you see my screen? Okay.
Yes, I do.
Nice. So, hello everyone. I'm gonna talk about two-level approach based on model checking to support architecture conformance check. Well, here's the summary. I have a little introduction to motivate the work, a little theoretical background to situate us, and the proposed method. Well, when we are implementing a software, developing a software, we have a problem known by architectural erosion. Well, we have the architecture that has been documented by the engineers and developers, and we have the real architecture that's being implemented and coded. And during the process of developing the software, these two architectures, they appears.
Excuse me, Bruno.
Oi. Oh, hello.
Sorry. Maybe it would be better if you use the full screen view.
Oh yeah, sorry, I forgot. Well, sure.
No problem. I think it's in the view menu. Yeah,
well,
great.
Yeah, great.
Thank you.
Thanks. So, the two architectures, the documented one and the implemented one, they diverge. And this caused some problems like loss of planned scalability, reduced demand maintainability, which makes the software hard to update and fix. We have loss of dependability and loss of reusability. So we want to avoid this problem. We want to avoid architecture erasure. To deal with this problem, we have the architecture conformance check. It aims to avoid disagreements induced by architecture erasure. And this is one, the conformance checking measures the accordance level between the design architecture and the coded architecture. And we reach the architecture conformance when there is no disagreement between the real architecture and the planned, the designed one. Well, here's a high-level definition of architecture conformance checking. It's a process of verifying if the decisions, the definitions, and the specifications made during design architecture phase are indeed being implemented when the software is coded. This verification should be constantly done while the software is implemented by the developers. And well, we have to perform this checking in some levels. In a high abstraction level, we have to check models, software connectors, communication interfaces. And in a deep implementation level, you have to check methods, classes, class packages, and control flow structures. Well, we need tools to support this process. They reduce the verification time, they reduce the costs, and they are more reliable than human analysis. So here we developed a formal verification method to add architecture conformance checking that focuses on requirements related to classes and methods. And we want to apply this method in a specific software version. And also, we want to apply it in a global point of view regarding all software versions. And here is the innovation of this work, because on literature, the methods, they are only concerned about one specific version. But here we are getting the global point of view, and we are taking into account all software versions in our analysis. And so summarizing the problem we are dealing with, giving a software model and a set of specifications related to its methods relationships and class relationships, we aim to check if the model satisfies such specifications along several versions. So the goal of the work is to propose a formal verification method able to solve the problem above while allowing the analysis of the specifications through the software development process along its various versions, aimed to be applying architecture conformance check. So what we want is a formal method that allows us to check specifications in a particular version, but also in considering all versions of the software. See how the specifications behavior throughout its process of development. The key ideas of the method we propose are a formal verification method to be used by architecture performance check in order to verify specifications related to classes and methods of a software. The analysis of the behavior of these specifications along the software development process, a logic with a new operator to represent specifications, and the application of model checking to verify if the specifications are satisfied by the system or by the model of the system. In order to model the system, we use cal graphs and version graphs, which I'll talk about later. And yeah, well, as I said before, taking into account the global level, considering several software versions, and not the analysis of a particular versions, is the great differentiation of this work. And we believe that this global analysis allows us to understand the changes that have been made, the scope, where and when they have happened. So it can facilitate management, facilitate tracking bugs, and the understanding of the project. For example, if a new member comes to the project, he can look at the history to understand how the software works. The theoretical background. Well, our main method here is the model checking. So to perform model check, we need a model of the system and a language to specify the requirements. The model will be made of cal graphs and software versions graphs, and the specifications will be written using a modal logic. Well, a modal logic, it's a combination of two other modal logics, a temporal logic, in which time is infinite, branched, and discrete. The temporal logics, they are suitable to model systems since they can get the dynamic aspect of the software, so we are able to check if appropriate properties are true in a given moment, is still true in a future moment or not. And we also use hybrid logics. Hybrid logic have a special type of propositional atom, the nominals, used to identify states of a model. Each nominal is true in a unique state, and we can use them to refer to a certain state in an easy manner. We're going to use the nominals to refer to a specific software version and identify each particular version. So we're going to combine these two logics, introduce a new operator, and then we have a new logic. Software versioning is the process of organizing each development state in a version and give unique identifiers to them. They are imperative to manage software development, and we have the version control systems as each to perform software version. Well, we're gonna get this history to create our model. I'm gonna show it next. Well, so we have these structures, these graphs, software version graphs, that maintain the history of versions. So we get the versions from the VCS, and we build these graphs. So we have a synthesis of all software versions in its history. Well, a version graph is a directed cycle-free graph, which the vertex set represents the versions of the software, and the edge set is the succession relation between these versions. So in our global level, we have this structure, and in our local level, to talk about a specific software version, we have the cal graphs. They are structures that code the relationships between the methods of a program. A cal graph is a directed graph, which the vertex set represents programming methods, and the edge means they call from one method to another. Thus, if a method A invokes a method B, there is a direct edge from the vertex A to the vertex B. They are built from the source code, and we have algorithms to perform this task. We didn't cover them in the work, but there's a reference for them in the literature. They already exist, so we can just use them. So, our proposed method. To achieve our goal, we create 2 levels of verification. The level 1 to deal with a specific software version. With this purpose, we use the call graphs. Each version has its own call graph, which use it to build the model for model checking. And we're gonna have to this level using the subscript in. In the second level, we deal with the global development process using the version graph. This graph gives us an overview of all software versions of a system, and it's used to build our model for model check. We're gonna have to this level using the subscript out. So we need to connect these 2 levels. To do so, we use a function that's gonna get a vertex from the version graph and gives the call graph of this version. And in the logic we create, we add a new connective to allow the communication between the 2 levels. So this connective, it's gonna switch the verification control from the second level to the first level. So we can deal with these levels in a homogeneous manner. And this makes our method a neat solution for the proposed problem because it's uniform. So, and the levels are communicating between each other. So it makes a neat solution. We have 3 main steps. We need to formalize the software specifications using the proposed logic. We have the documentation of the architecture, so we can write the specifications using the logic from the documentation of the architecture. We need to model the system according to the structures I'm going to explain next, the call graph and the version graph. And then we now have a model and a set of formulas of a formal language. So we can apply a model checking algorithm to decide if the model satisfies or not the specification. Well, we're going to represent the call graphs as script structures. So we'll have the set of states that represents the methods present in the software, which is the vertex set of a call graph. We're gonna we have the edges, the set of transitions. So there's an edge from state A to state B if the method represented by A calls the method represented by B. Is the edge set of the call graph. We also have a label function, and we're gonna label each stage with the method with a propositional atom, which stands for the method that this state represents, and the class that has this method. We also have a set of propositional atoms, and well, we have a propositional atom for each method and each class being assessed. And we also have an initial state. When we apply the model check, we take this state as the initial one. So here's our first structure. Here's a simple example. We have two classes representing geometric figures and methods to calculate its areas. So it's quite simple. The main method in the class A calls the area of a square figure and the area of a circle figure. So we have a edge from the main method to the area method of the square and the area method of the circle. And since our logic is infinite, we add a dead state just to indicate that this method doesn't call any other methods. So, and the dead state has a loop to indicate that the execution flow has ended. So the version graphs as crypto structure, it's basically a crypto structure, but we enhanced it with 4 more elements. So we have the set of states. Each state represents a software version. the set of edges will say which versions are successors of a particular version. The label function here can be used to code extra information about the version graphs through propositional atoms, so the engineers can codify any interesting information in propositional atoms and put them in the state. We also have the initial state, which represents the first version of the software. We're going to have a set of nominals used to identify each version. We have ways to identify a software version. The famous one is called semantic versioning. We use a series of numbers to indicate the version, and we increment these numbers according to the level of change, but I didn't cover this point here. We have a set of alpha graphs under analysis, a function that links the nominals to the corresponding vertex, and a function that links a vertex of the version graph to the corresponding cal graph. So this version will give us what is the cal graph of a particular version. So the version graphs are cycle-free. We can walk through them only in one direction. This information is important when we are writing the specifications because it uses sometimes to prove the soundness of the resulting formula. We assume that we have only one initial version and only one final version, and that from the initial version we can reach all other versions. And each path in the version graph stands for development branch. And the cryptic structure preserves this feature since it's just codifying the version graph with some additional features. So here's an example of a version graph. We have here a final version, which we put a final propositional atom to identify it, and a discarded version. We can have discarded versions that we just abandon its development, and yeah. So here's the idea of a version graph. We're gonna walk through this graph, verifying specifications. We can get in a particular version, getting the cal graph by means of a function and apply model check to check specifications on it. So, well, here's the logic that we propose. It has two levels. One level to be evaluated to the cal graphs. So we have here traditional connectives from CTL, a famous temporal logic. We have connections to talk about the future, some to talk about the past, and the Booleans connectives. So yeah, and in the second level to talk about version graphs, we have basically the same connections. We don't have the past connectives because we don't need them. But the interesting thing about the second level is that we have the nominals I and our operator which allow us to jump to a specific version. This one here. It allows us to jump to a version which has nominal I, and we have the in operator, which is the operator responsible to switch between the two levels of verification. So yeah. Here's the semantics. Well, we're gonna have the version graph as a cryptic structure, and well, For the Booleans, operators and the temporal operators are the semantics that we found common in literature. Operator to talk about the next state. Operator to talk about a state in the future. Operator to start checks properties in a path. Here, operate the nominal, so we can identify a version. Here's the jump operator, which allows us to jump the verification to a version identified by the nominal I. And here's the in operator. We're gonna get the call graph associated by the vertex in the version graph by the function C, and we're gonna apply the model checking in this call graph. So here we switch the verification level from the global one to the local one. And once this verification is done, we switch back to the upper level. So here in the level one, we talk about the past because we found some specifications start asking for it. Yeah, the semantic is just as the common temporal logic semantics, just start, we have added this new operator to allow the communication between the two levels. So here's basically what I
just notice, Bruno, because the time has run out, the 20 minutes. So please, could you conclude?
Okay. So, well, I have put here some examples just to show how the method works in practice. But, well, we can use it to check famous specifications related to some architectural partners. Well, I'm gonna just jump, and the conclusion we start. Well, this method, it uses a kind of logic that is familiar to software engineers, which make it easy to apply in real-world scenarios, other than other methodologies found in literature, like this one proposed by Harold, which is Botha logic, and it's way more cumbersome to use and understand. So, by the example that we analyze it, the size of the forms are small and they could be easily read by humans. We have this two-level approach that is an innovation that gives the engineer a manner to analyze the global behavior of the requirements being assessed. So we think that this is the most interesting thing about this work. And yeah, and this method, it works like a framework, since we can switch the structures, like we can switch the call graphs to other structure to analyze other properties. And well, we can, perhaps we must to change the logic, modify the algorithm, but yeah, it works like a framework because we can just switch the structure, and by doing so, we can check other features about the software, not just the ones related to methods and classes. It helps. This is why we think that it's a really flexible method. And I didn't talk about the algorithm, but it's a polynomial time algorithm, so this is nice. And yeah, we think that this methodology can be really useful to architecture conformance checking. So we can apply it to develop high quality systems. Future works just use it as a framework and check on other structures and improve the complexity of the algorithm, because we think that it's possible to lower the degree of the polynomial of its complexity. Here I just put some reference, and yeah, that's all. Thank you.
Okay, thank you, Bruno, for your presentation. Interesting work. You have two levels of two ways to model the architecture, and I will ask if the audience has questions, has questions to make. Someone has questions to. Somebody raised the hand. Oh, let me see. Nobody. I can start. Okay, I can start making I would like a clarification, because you present many requirements for the architecture, like scalability, reusability, and so on. And you say that the requirements that your framework can verify are requirements related to class and methods. And so I ask if you are you can really deal with any kind of requirement, like non-functional requirements, like this one, scalability, for instance, using your framework, or it's necessary to extend or to improve anything to deal with this kind of requirement, architectural requirement.
Well, we are assuming that when the architecture is designed, it has a series of constraints, requirements, and specifications that, if correctly implemented, will allow the software to be easy to maintain, will guarantee scalability, and the other features. So our method is a tool to get this well-designed architecture and checks if the implemented architecture is indeed implementing with the decisions and the design decided by the engineers. So if so, we can say that the software will have the features proposed in the documentation. And if not, you will need to be fixed to fit the specifications. So our method per se doesn't, it cannot assure those features. It can only assure that if it has the features in the documented architecture, these features will be in the implemented architecture. So they will indeed be in the software, not just in its documentation. It will be indeed in the code source, let's say like this.
Okay, let's see if we have more questions. Not yet. No, let me put another question. You presented that you have two levels, but and somehow you can link these two levels, and you can make verifications considering both levels. If I
yes.
Yeah.
Yes.
Okay. So do you think that this can raise some scalability issues consider the size of the model? If you do you think?
Yes. Actually, our structures, the version graph and the call graph, they are well behaved, let's say. So model check algorithms for model check in general, they have to deal with random cryptic structures. So they can have any part, how can I say? Well, they are general, so we can get any kind of cryptic structures. But here we have a well-behaved structure. It's a directed graph, so which follows only one direction, and we can also, we won't analyze the whole system in one time. We can separate specific points and analyze them each at a time. So by doing so, we will have well-behaved structures that are not really big, or so we can avoid the explosion states problem that happens in model check. So yeah, since we can always separate specific parts of the system, and we have a well-behaved structure, we actually can get a better performance than model checking in general.
Okay, let me see. We have maybe okay. no more questions, I think, not to have. So let's thank you, Bruno, for your presentation.
Thank you.
And if you could, the screen sharing, if you could release the sharing. And
I think I already did.
Or maybe the next presenter, it's able to share his screen. If it's present. Okay.
Are you able to see my screen?
It's the image of your screen is not yet showing I cannot see yet, but maybe it's loading.
Your screen sharing is paused.
Sorry?
It is showing your screen sharing is paused. Even if I resume, it is not working. New share. Now, is it working?
Oh, now it's working. Yeah.
Oh.
Okay. So let me. Now we have the third work of this section, the statistical model checking for traffic models, and the author is present, and he starts his presentation now. If you are ready, you can go on. Okay.
Thank you. Good evening to all. I am Thamilselvam from the Department of Computer Science and Engineering, Indian Institute of Technology. So this work is jointly done with my supervisors. The talk of the today is statistical model checking for traffic models. We will look into the outline of the talk. We will just start with the base background and motivations and the tools which we use, then the integration of the tools, and some more results. Finally, we will see the future direction. And we will see, if we consider the city traffic, in the city traffic, whatever available in the traffic simulators, they support some bare minimum level statistics we can collect from that simulators. All simulators has the capability to give some statistic average, for example, average of duration or waiting time or time loss or departed delay. These are all the things. So if you want to find out some simple query, what is the average waiting time or delay, then we have to run multiple times the simulators and collect the results. We have to show. How about this kind of complex queries? Suppose what is the probability that an emergency vehicle reached near hospital within 10 minutes under some given traffic conditions? Based on the traffic scenarios, this will be different probabilities will be given. These kind of queries, we cannot get the result from the traffic simulator itself. Even for some complex queries, what is the probability? What is the traffic volume at intersection 1?
Sorry for interrupting, but what we can see is only the first slide. Maybe has shared a different screen that you are presenting.
Let's see.
One suggestion, it's you can put it in full screen first, and then you share the screen.
Now, are you able to see next screen?
Perfect.
Okay, now everything is okay. Can I continue? Hello? Can I continue? Is that
yes? Sure.
Okay. Then let me go. just we see the background about the talk which we are interested in. So if we consider about any traffic city traffic simulator for simulating various vehicles in the for traffic management in order to control traffic signals and other things, accident management, everything. So the basic, the statistics which will be given from the traffic simulator is like what is the waiting time and what is the time loss or departure delay. These are all some basic requirement will be collected. For example, if we want to find average waiting time, so we need to run it multiple times with different speeds and make it average. About some complex queries, like what is the probability that emergency vehicle reached near hospital within 10 minutes under given traffic conditions. This is not direct information getting from the simulators. And also, if we consider about what is the traffic volume at which intersection 1, which causes the deadlock in intersection 2. These are all the informations we might be interested in. Traffic engineering or any traffic related persons might be interested to get the information about these kind of things. But there are any traffic simulators available which will not be given directly these kind of information. Suppose if we are able to combine our statistical model checking from the computer science and the traffic simulator, which are this kind of gap will be fulfilled. So we decided to tackle this kind of problem to combine the statistical model checking existing available with the traffic simulator and try to get the required queries and these kind of things. So what is statistical model checking? We know the statistical model checking is the combination, combines the simulation and the statistical model. For example, it will come with the confidence interval and prediction interval, that SMC, and the SMC simulation will run this system many times. We will get the execution trace. Along with it, if we give specification, and the specification will be checked against that trace, whether the property is satisfied or not. This is the simple skeleton of that SMC. They are using Monte Carlo sampling for one of the systems, and for a confidence interval, they are using Chernoff. The traffic simulator, which supports normally the car following model, in which case we have checked with the car following models and the lane changing model. The car following model is it's a method used to determine how vehicles follow one another on the roadway. The higher speed decides the space between the vehicles should be high. Parameters, safe distance, and which are all the theories involved. So we will consider 3 car following model in our experiment: gross, Rideman, and intelligent to drive. And the lane changing is subject to current vehicle need to be changed whether right or left. The selection will be based on the acceptance gap and other things. So we will consider for our experiment LC2013. This is one of the lane changing model, and the SL2015. So in order to fulfill that requirement, we combine the 2 tools, one from statistical model checking, simulation of urban mobility. The statistical model checking tool, the Multivesta is the tool which supports statistical model checking, and it is coming from Vesta family, and it is the Java-based package, so it can directly integrated with the discrete time simulators, and it supports the quantitative temporal expression logic, that is PCTL. Even it supports PCTL CSL also. And if you think about the microscopic traffic simulation, the Sumo supports online interaction with the Teresa, and it supports several car following and line changing models. So the integration of Multivesta and Sumo. So the integration of Multivesta and Sumo done through Sumo State. This is one of the program. And since Multivesta is in Java and Sumo is C++, we combine some native languages, native method with the Sumo State, through which we can, for example, any discrete event simulator, if it wants to communicate with the Multivesta, this is statistical model checking tool. So it requires some more function. three function is mandatory. One is set simulator for new simulation. It means whenever this multi-tester needs to run the recurrent discrete event simulator, it has to set some random number and start with a new experiment, new trajectory need to be created. And second, perform one-step simulations. After performing one step of simulation, it needs to observe the required observation. What are the things need to be observed? So we need to run one step from multi-tester. So these are all the things need to be supported from the discrete event simulators. And the R value of int is the real value of integer. This value, we have to write it based on the simulators and our requirement. In our case, if R value of 0 indicates current time. So if we think about this sumo simulation, the time is something, whenever we press this button, it will increase the time 0, 3, 0, 4. Based on that, the cost simulation and other things will work. So same way, we have to set what are the observation point we needed to observe. For example, R value of 7, we will think about CO2 emission. What is the CO2 emission in the current state of the simulator? These are some more results. Before going to the results, we will talk about the setup, environment setup. We set simple 3 traffic intersection, and we will consider emergency vehicle and normal vehicles. Normal vehicle is normal vehicle which does not have any priority. For example, while crossing the traffic signal. But in the emergency vehicle has the priority. It has, even if it is a red signal, it may cross the signal. It may cross the traffic. And these are all the parameters we consider into the multi-vector client. If we think about this alpha and the delta, these are all important parameters for the confidence interval. So we set delta value equal to 2 for non-probabilistic queries and delta value 0.1 for probabilistic queries. And if we consider about simple queries, estimate the expected CO2 emission within the simulation time. So this query we can formulate using Cortex in this form up to 100 seconds, find out the CO2 emission in the simulator. So based on the various combination of car following and lane changing model, so cross SL and Weidelman SL and intelligent driver IDM SL cross LC, these are all the pictures. We can get the result from the simulators. If we think about some complex queries, the traffic volume at intersection I1 is less than until the point the traffic volume is high at the intersection I2. In our case, if we consider, for example, 15 is the traffic volume, we consider around 500 meters from the traffic junction, count the number of vehicles available. So the probability that the traffic volume at I1 is less than 15 until the traffic volume I2, intersection 2, is greater than 20. So we can formulate the queries and we can get the result. And if you think about the future directions, we can use this tool chain for studying microscopic traffic simulations other than lane changing and car following models, because we consider for simple scenarios to test the integration part of this statistical model checking and the traffic simulators. If you are able to further in future, one can easily check a lot of varieties of parameters available in this traffic simulators that can be done using this tool chain, and more penetrating and insightful queries on large systems for impactful analysis, because this is statistical model checking. It can support very large scale, and the scalability is very huge. So we can consider the huge city with thousands of intersections and the traffic signals can be considered, and we can queries more insightful queries. Like these are some basic queries we have. These are not even papers support some more extended queries, and we can create more nested queries and find the more insightful from the traffic scenarios. So the available interested reader also can go, that GitHub link is available, or our source code is available. You can download it and run it.
Thank you for your presentation. Let me see if we have questions. The audience? Not yet. So I will start. I was wondering, because your approach builds a model using information from a simulator, yeah?
Yes.
And use this model to verify some traffic conditions, some parameters that are standardized and relevant for traffic issues. Okay. So yes. My question is, if you have, how can you be sure, how do you know that you have enough information for a model? Yeah, because it comes from a simulation. What criteria do you use to know that we have a good model to verify properties? Can you talk a bit about this?
Yes. For example, in the traffic simulators, whatever the simulator done with some based on theories. So its output is surely from the practical implementation. So we are running that simulator multiple times. We are collecting information from that, and we are checking that information, whether whatever the questions we asked satisfied or not.
Okay, I see Sergio. Thank you for your Sergio wants to has a question too. Okay, can go.
Yes, thank you. That was a very interesting presentation and a very nice idea. I liked it very much. I actually had a student that was working on traffic models and model checking, but we just created the model and ran the model checker. Never thought about combining a traffic simulator with a model checker. So that was nice. I was wondering, this seems applicable to other kinds of simulators. Have you thought about using that for other kinds of applications?
In Multivista, they have a lot of other simulators combined. Any discrete event simulator that can be coupled with Multivista.
I see. That's interesting. Yeah, the first one I would try because of my work would be a biological system simulator. But yeah, that's an interesting thing. So I wish you success, and let's hope to see more of your results later on. Thank you.
Thanks.
Okay, let's see if we have more questions. No, but I have a very short another question. I'm curious about the verification time, because you put a table in your paper.
Yes.
You showed the time for the verification until 60 seconds, something like this. But how long is to complete? Just to give an idea of the computational effort to analyze this example that you showed with 3 intersections in a line.
Yes. In 3 intersections, based on the queries we found, if the queries in confidence interval is very small, and it will take more time. And for example, within 3 minutes, if it is to be completed, if we give a confidence interval about 0.8 or something, if we reduce the 0.5, it will take 30 minutes. There is a time complexity in the trade. The computation, that confidence interval and that running time, there is a trade-off between both. If we need more confidence, then it will take more time.
So you can adjust this trade-off of
these parameters.
Okay. If you want to scale, so you can reduce
Yes.
okay, good, thank you. Okay, so thank you again for your presentation.
Thanks.
We had a problem with the first presentation because the connection, a problem with the connection, and Nils is back, and we have, I think the presentation was about 40 minutes, so 14 minutes, so I think there is enough, there is 6 minutes at least for you to use to complete your presentation. Nils, if you are still
Maybe,
able to present.
Sydney?
Okay.
Yeah, I
Okay.
bought some data and I'm using my phone now with the data. Maybe it will work from my side. We can.
Maybe I can show you the video from my computer, and then you can answer questions. Is that okay?
Okay, that's also fine. Yeah.
I'll try to share my video screen. Just a minute. Can you see it?
Yes.
I'm gonna play it, okay?
Yeah. You must.
A demand function D that assigns to each agent the amount of resources it needs to allocate over time, and an accessibility function ACC that defines for each agent the subset of overall resources that it can access. The following types of actions exist. Request actions, where an agent A requests a particular resource R. Release actions, where an agent releases a particular resource R. Release all actions, where an agent A releases all the resources that it holds. And idle actions, where an agent does nothing. A tuple of actions, one for each agent in the system, is called an action profile. And we assume that in each round of the system, each agent chooses an action, and the corresponding action profile gets executed. The dynamics of a multi-agent system result from states and transitions. Formally, a state of an MRA is a function S that assigns to each resource in the system either an agent or the value null. If an agent is assigned, this means in the current state this agent holds this resource, or if the value null is assigned, that means in the current state the resource is unallocated. A transition of a multi-agent system is a triple consisting of a current state S, an action profile AP, and an successor state S prime. An action profile AP must be executable in the current state S. For our systems, we have defined executability as follows. An agent can only request resources that are available in the current state. If an agent has satisfied its demand in the current state, then it must release all resources that it has allocated. And an agent can only idle if no accessible resource is currently available. These execution rules are also called the protocol of the multi-agent system. Now we look at successor states. After the execution of an action profile AP, the successor state S prime is defined as follows. Released resources become available in the successor state, and if a resource is requested by a single agent only, then this agent will get the resource in the successor state. Otherwise, if multiple agents request this resource, no agent will get it. How the states of the system change based on the execution of action profiles is what is called the evolution of the system. What we have here on paths and strategies is mainly a repetition on what we introduced earlier. A path is a sequence of transitions, where each transition is a triple consisting of a current state, an action profile, and a successor state. A strategy of an agent A is the function alpha A that assigns to each state of the system an action to be executed by this agent in this state. And a joint strategy of a coalition A is a tuple of single strategies, one for each agent in the coalition. Finally, we define what the outcome of a coalition strategy alpha capital A against a set of opposition strategies sigma starting in some state S is. It is a set of possible paths, pi, with the parameters S, alpha, A, and sigma, that start in the state S, when the coalition A follows the strategy alpha A, and B follows some strategy from the set sigma. If we assume that the set sigma contains multiple strategies of the opposition, then it becomes obvious that the set capital pi can contain multiple paths. Now we come to the definition of the MRA model checking problem in the restricted case. In a given MRA, a coalition A has a strategy to achieve the goal phi against the opposition strategies in a set sigma if the following holds. There exists a strategy alpha A such that for all paths pi in the system that start in the initial state as 0, where the coalition A follows the strategy alpha A and the opposition B follows some strategy from the set sigma, every agent in the coalition A will eventually reach its resource allocation goal. In our approach, we make use of bounded model checking because it can be reduced to the Boolean satisfiability problem. And in bounded model checking, we additionally have a bound K, and then the question is, does the coalition has a strategy to achieve the goal within K steps? Bounded model checking can also be used to perform unbounded model checking if all possible bounds up to a completeness threshold are considered. For bounded model checking problems with regard to multi-agent systems, we have defined a propositional logic encoding. We construct a propositional logic formula for which the following holds. First, we have the model checking theorem that states that the propositional logic formula is satisfiable if and only if the encoded bounded model checking problem holds. And second, we have the strategy synthesis theorem. If the formula is satisfiable for some truth assignment alpha, then alpha exactly characterizes a winning strategy of the coalition. Now we get back to the big picture of the iterative approach, and we can see that all the necessary model checking runs can be performed via satisfiability solving. If the encoding of a model checking problem is satisfiable for some truth assignment alpha, then alpha characterizes a winning strategy. So also strategy synthesis works sub-based here. The overall encoding is divided into the following parts. We encode the initial state of the system for time step 0. We encode the possible evolution of the system for all time steps between 0 and k, and then we have an encoding part that ensures that the coalition A adheres to the protocol at all time steps. Moreover, we have an encoding part for the goal reachability property to be checked. These encoding parts are constructed based on the following basic encodings. An encoding that an agent A holds a resource R in a state at time step t, an encoding that an agent A has reached its goal in the state at time step t, an encoding that an agent A performs an action act in the state at time step t, and an encoding of a strategic decision of an agent to perform a certain action in a state S.
To give you a bit of an idea how the encoding looks like and works, here you can see the encoding of the evolution from time step t to t+1. Based on the actions that the agents in the system have chosen at time step t, the allocation status of a resource R will be updated for time step t+1. So this evolution encoding will be only satisfiable for truth assignments that characterize a valid transition in the system. We have implemented our approach on top of the SAT-solver picosat, and in experiments we were able to synthesize winning strategies for coalitions in multi-agent systems with up to 8 agents. As future work, we plan to extend our approach such that not only winning strategies can be synthesized, but also optimal strategies with regard to some quantitative measure, and strategies that are a Nash equilibrium for all agents in the system. I conclude my talk with the big picture of our approach again, and I thank you for your attention.
Okay. So this time you managed to conclude. Okay, good. No problem with network. We have. Let me see if we have questions. Sergio is raising his hand.
Yes. Very interesting work. I was wondering what kind of practical applications would this be applicable to? And there are some limitations on your modeling, which is natural. This is a very hard problem. And I was wondering if you plan on making a richer model and if you think that's going to work.
Just to unmute your microphone, Nils, if you, I don't know if you are trying to speak. Nils is saying that
he didn't, he didn't hear. I suggest to put the questions in Discord, and then he try to answer later.
Okay, we can do that.
Okay, thank you for the question, and thank you, Nils, for for presenting your work. Yeah. So the suggestion is to put in Discord, so we can also discuss the last asynchrony. Okay. Okay. So this and the second technical section. Now we thank you all the audience and the presenters. Now we have a break, and after we have a meet, but as a meet, I think just only for the
sorry, I don't know if you can hear me, but on my side, I still have very strong connectivity problems. I can't not.
Okay, don't worry, Nils. You can put the.
If you ask your questions by Discord also, then I would answer them there.
Okay. Don't worry. Okay. Can do. Okay, thank you again.